In this section, we're going to go over confidence interval, but when we do not know what our population standard deviation is. And if you kind of recall from the previous section, we were able to compute confidence interval with the population standard deviation given. So in here, it's going to be a little bit different. First, I want to talk about is something called a student t distribution. So in order to use a normal distribution to find confidence interval for a population mean, mu, we need to know what the value of our sigma is, or the population standard deviation. And that's what we did in the previous section. But what happens when we don't know this value? So when we do not know what our population standard deviation is, we use the sample standard deviation, S, to kind of estimate the population standard deviation, sigma. So we're going to replace sigma with our sample standard deviation. And in most cases, in the real world, they actually do this quite often because we don't know what the population standard deviation is most of the time. So that's why a lot of people just use the sample standard deviation S. But there's a couple things you have to keep in mind. So when we use S to estimate sigma, the sample distribution for X bar follows a new distribution. It doesn't follow like a standard normal curve anymore. It follows something called a student t distribution. So when learning about student t distribution, we need to know something called a degree of freedom. When constructing a confidence interval for a population mean, the number of degrees of freedom for a student t distribution is just one less than the sample size n. So in other words, the number of degrees of freedom is just going to be equal to n minus 1, where again, n here is your sample size. Okay, so a couple properties for student t distribution. The distribution is symmetric, about the mean 0. The distribution kind of depends on your degree of freedoms. And one interesting note is that as the degree of freedom increases, this new distribution, the t distribution, begins to actually look like a normal distribution as your degree of freedom increases. And the area under the curve is 1. So one note, and this is kind of important. This is kind of the whole theme of this section. This distribution has t values that are similar to z values of the standard normal distribution. So the goal of this section is to estimate the population parameter mu, but we're going to use t values instead of z values. So that's the key thing here. And then I put a little picture here to kind of illustrate this. Increasing your degree of freedom will begin to look like a normal distribution. So if you look at this line here, this has a degree of freedom of 1. And if you look here on the black line, this is your standard normal curve. So notice as t increases, you get closer and closer to your standard normal curve. And that's the idea here. If you kind of recall from the previous section, in order to compute confidence interval, we need essentially two things: a point estimate and a margin of error. And that's the same idea here. But to compute our margin of error, we need a standard error and a critical value. So here, our critical value is going to look a little bit different. So critical value of t of alpha over 2. The reliability of point estimate is measured by the confidence level, which is 1 minus alpha, so that kind of stays the same. The critical value, denoted for t of alpha over 2, is the number such that the area under the student t distribution, between negative t over alpha over 2 and t alpha over 2, is equal to the confidence level. So again, this is a student t distribution. And this will have an area of your confidence level, and your critical value is just the points, or the location where, if you took the area between these 2 points, you're going to be equal to your confidence level. So let's say your area here, you were dealing with a 95% confidence level, then the area here will be 0.95. But how do we actually compute these? How do we find our critical values? We're going to use something called the student t distribution table. So here, to find the critical value, t of alpha over 2 for n minus 1 degrees of freedom, look for the given values of the degree of freedoms. I'm just going to call it df, just to shorten it, and the confidence level, 1 minus alpha, in the table. So for example, let's say you want to find a critical value where your confidence level is 95%. So the area between these two values is 0.95. And let's just say, for example, that your degree of freedom was 9. Well, we're going to use something called, this table here is table A3 in your textbook. You can also find it on Blackboard if you can't find it in your textbook. But what it is that you want to look for your degree of freedom. And here in our example, our degree of freedom is 9. So you look at 9 here. And then you want to look for which confidence level are we dealing with. In this example, we use 95% confidence level. So if you look down here on the confidence level, you look at 95, because that's what we're looking at. And you want to see where they intersect. And they intersect right here at 2.262. So we could say that the critical value here is 2.262 and negative 2.262. So you just found your critical value for a student t distribution. And here's a little like chart just to remind you. So again, confidence level will be here, and the degree of freedom will be here. And where they intersect is your critical value. Other things you want to look out for is that if the desired number of degree of freedom is not listed in the table, then you have a couple of choices. If the desired number is less than 200, so if your degree of freedom is less than 200 and it's not in your table, then you just use the next smaller number in the table, and that will be your degree of freedom. If the desired number is greater than 200, so let's say your degree of freedom was like more than 200, then we actually use the z value found in the last row. So if you look at the table here, if it's greater than 200, then we actually just use the z table, because if we remember, if our degree of freedom is bigger and bigger and bigger, it actually starts to approximate a standard normal curve. And that's why we were able to use z values instead of t values, because it's approximating a normal curve. But if it's less, then we have to use this chart. Let's practice finding critical values for a specific confidence level and degree of freedom. So let's say you were given a confidence level of 99% and your sample size was 5. First thing you want to do is actually compute your degree of freedoms. So your degree of freedom is just n minus 1, which is just 5 minus 1, which is 4. So then you go back to your table, look at your degree of freedom. Here, in this case, it's just 4. And you look at which confidence level you're working with. In this case, we're working with a 99% confidence level. So you want to see where do they intersect. And they intersect right here. 4.604. So our critical value, T of alpha over 2, this is just going to be equal to 4.604. How about for this one? Let's say your sample size was 91. So your degree of freedom will be n minus 1, which is 91 minus 1, which is 90. So then you look at your table. Let me just erase this real quick. So you look at your table. You want to see where 90 is in your degree of freedom. So you look, and look at that. The 90 is not in your table. So what do? Well, if you look back, if your desired number is less than 200, which is this, use the next smaller number that's on the table. So in this case, the next smallest number of 90 is going to be 80. So we're going to actually use 80 as our degree of freedom. And since we're working with a 99% confidence level, we go to 99 and see where they intersect. And they intersect as 2.639. So that's going to be our critical value. So here, our critical value is going to be 2.639. How about this one? We have a a confidence level of 99% and a sample size of 600. So that means your degree of freedom will be n minus 1, 600 minus 1, or 599. So let's see. Notice that 599 is not in our table. So since 599 is larger than 200, we actually use the z-values, because since our degree of freedom is so large, it's kind of approximating a standard normal curve. So we're just going to use the z-value for our critical value. So this will be, if you look at 99%, it's going to be it's going to be 2.576, because a 99% confidence level will have a z-value of 2.576. So here, in this case, our t of alpha over 2 is going to be the same as z of alpha over 2, which is 2.568. Now that we have some practice computing our critical value, let's learn some of the steps to actually computing our confidence interval. Here, before we even start computing our confidence interval, we want to see if all of our requirements are met. So we want to see if it's obtained by a simple random sample of size n. We want to compute our x bar and s if they're not already given. And of course, we want to see if our sample mean distribution is normal. And how do we satisfy this? Again, we could satisfy this by checking one of two things. Is x already come from a normal distribution, or that the population is approximately normal? And if the sample size n is big enough, is greater than 30. If one of these satisfied, then we could say that our sample mean distribution is about normal. So here are the steps to actually computing confidence interval when we don't know our population standard deviation. One thing you want to do is compute the sample mean and the sample standard deviation s if they're not given. Usually there are. You want to find the number of degrees of freedom, n minus 1, and the critical value. Then we want to compute the standard error In this case, it will be your sample standard deviation over the square root of your sample size. And then once we have your standard error and your critical value, then we're able to compute your margin of error, which is going to be equal to your critical value times your standard error. So again, this is just your critical value. And this is your standard error. Once you have your margin of error, we're going to use your point estimate and construct the confidence interval. So this is just x bar minus e is less than mu is less than x bar plus e. So it's kind of very similar to what we did in an earlier section. But finally, we want to actually give the interpretation. And again, this is really important. And we usually say that we are, let's say, for example, we're using a 95% confidence level. So we can say we are 95% confident that the population parameter is between the two values found. So let's, for example, here, let's practice computing our margin of error. In this case, we're using a 98% confidence interval. If the sample standard deviation is 18 and the sample size is 160. So here, our sample standard deviation, since this is a sample, we call this S. This is equal to 18. And our sample size, N, is 160. And we're using a 98% confidence interval. First thing you want to do is compute your degree of freedom. So degree of freedom is just n minus 1 or 160 minus 1, which is equal to 159. So then, in order to find your critical value, t of alpha over 2, we need to know our degree of freedom. So we can look back at our table and look at where 159 is located. Since it's not in our table, we just use the value smaller to it. So here, 100 is the next smallest number. So you look at this row, and since we're dealing with a 98% confidence level, we look at 98, and thus we found our critical value, 2.364. So this will be 2.364. We also have to compute our standard error, which is S over square root of n. In this case, it is 18 over square root of 160. Equal to 1.423. So that means our margin of error, this is the critical value times your standard error. This is going to be 2.364 times 1.423, which is going to be equal to 3.364. So this is your margin of error for a student t-distribution. Now that we have some practice with margin of errors, let's do an example of actually computing a confidence interval. So here, let's get rid of this extra example. So here, the General Social Survey is a survey of opinions and lifestyle of U.S. adults conducted by the National Opinion Research Center at the University of Chicago. Here we have a sample of 123 people aged between 18 to 22 reported that the number of hours they spend on the internet in an average week. The sample mean is 8.20 hours with a sample standard deviation of 9.84 hours. Assume this is a simple random sample from a population of people aged between 18 to 22 in the United States. Okay, so First, we want to are the requirement for constructing a confident interval met. So that's the first thing we have to check. Notice that we have a sample size of 123 people. We have the sample standard deviation, which is 9.84, and we have a sample mean of 8.20. Notice that our sample size, n, is 123. Since this is greater than 30, we could say that our sample mean distribution is about approximately normal. So we could say that all the requirements are met. And we're also given our sample standard deviation and our sample mean. So we're all good. So we're able to compute a confident interval. Let's find the sample mean and sample standard deviation. So then this is pretty straightforward. S is equal to 9.84 and X bar is equal to 8.20. We want to find the number of degrees of freedom and the critical value. And I forgot to mention that we're dealing with a 95% confidence level. So here, our degree of freedom is equal to n minus 1, which is 123, minus 1, which is 122. We need to compute our degree of freedom in order to find our critical value, t of alpha over 2. So now we could look at the table and see where 122 lies. So you notice 122 is not in the table, so that means we have to choose the next lowest value, which is 100. And since we're doing a 95% confidence level, our critical value here is going to be 1.984. So our critical value is going to be equal to 1.984. Next, we want to compute our margin of error. So this will be E is equal to our critical value times our standard error, which is S over the square root of n. So this will be 1.984 times 9.84 all over the square root of 123. So this will be equal to 1.760. So now we're able to construct our 95% confident interval. So this will be X bar minus our margin of error is less than mu less than X bar plus our margin of error. And so this will be minus 1.760 is less than mu is less than 8.20 plus 1.760, which is 6.44 is less than mu is less than 9.96. So now we just constructed our 95% confident interval. But what's important is actually interpreting our result, because again, if we did all this computation and we're not able to interpret, then there's not really much use for it. So we could say that we are 95% confident the mean number of hours per week spent on the internet by people 18 to 22 years old is between 6.44 and 6 point, oops, and 9.96 hours. Now notice that I'm tailoring my interpretation by what the problem is asking or what the problem is saying. So the problem was saying about people between 18 and 22 and how long they spend on the internet per week. And that's why in my interpretation, I mentioned that. So your interpretation, it's always tailored to what problem you're working with. And just because of time, I would actually do this problem on your own. This is actually a really good problem that might be on the good practice for the exam coming up. I'll post the solution online. It should be on like filled notes on Blackboard. So just keep a look at that.